All right. One last attempt at screen flow. If it doesn't work today, I'll be annoyed. All right, so last lecture, assignment 2, you're already working on. There's a quiz due today. I didn't check how many people had done it. Then there's another quiz that'll be out tomorrow. And of course, my experience is out. So give me feedback. I can give myself some feedback. I'll tell you one thing I'm never going to do again is teach 2 courses in one semester, especially when one of them is an extremely large first course. Just both. Having to do both, especially when you got 4 hours on one day, it's not helpful. Not that I had 4 hours today, so that's good. All right, so today I'll talk about what I've called non-classical DBMSs, and then talk about the exam. And all I've got to do for the rest of the semester, given that I'm not lecturing anymore, is do lots of marking. Oh, all right, here's some DB nerds. Who are these people? Well, I should start giving prizes for all of them. Yeah, good. Yeah, yes. Any names? Pick what if I point the thing at that guy? You'll go, I don't know, and neither do I, so that's all right. But I can name 4 of them. That one up there, Tom Lane. If you've been looking through the Postgres documentation at all, his name would have cropped up because he's probably the main developer. He gets all the patches, sticks out the new versions of Postgres. Let me see. This guy is Josh Burkus. His name crops up a bit on the Postgres documentation as well. This guy is Bruce Momjian. He's the PostgreSQL ambassador or whatever. He wrote the original textbook that involved Postgres. And this guy is an Aussie. His name is Gavin Sherry. I'm not sure whether he's still here, but he certainly was here a few years ago and actually gave one of my lectures. So he knows about Postgres guts as well. And because it's the last lecture, I decided to do 2 nerds. Here's another one. Gosh, I look a bit young there, don't I? It's a bit scary. Anyone want to guess how many years ago that was? Oh, damn good guess, you know. I just realised that it is. Where am I, though? That's the question. Nice buildings. Yeah, that's a good start. But it's actually Oracle headquarters, which, if you look carefully, you can up there. I never got invited in, but went and had a look anyway at the outside. Okay, so let's get on with the final push. Right, so I'm going to talk about non-classical databases, but what are the things that we know about classical databases? And to some extent, this is a little bit of a reprise from last time, but basically relational databases, we deal with sets of tuples. Tuples are sets of atomic values. You can't have structured values inside a tuple. Of course, most databases extend that anyway. Postgres has array values that you can stick inside tuples. You can compare data values precisely. You can use logical expressions to describe what kind of tuples you want or what tuples you want, tuples matching what constraints. You can do pretty much all of your data manipulation with SQL. Occasionally you need to fall back to a bit of procedural programming wrapped around SQL, and that would either be PLPG SQL or some kind of application that you're writing, Java or Python, PHP or whatever, interacting with the database, asking queries, and then doing things with the data. Databases spend a lot of time dealing with transactions and getting it right, and most of the applications that use relational databases, this is critically important. Banks, blah, blah, blah. Data stored on disk, obviously, processed in memory, that's still going to be true even with non-classical databases, although there are some that deal with the fact that we've now got extremely large main memory and we've also got solid state devices for doing bulk storage. Similarly, a lot of the work has been predicated on the fact that transferring data between disk and memory is the most expensive thing that you ever do. All right, so what do we want? What do modern database applications want? They often say they want more flexible data structuring mechanisms. Bah! What's wrong with tuples and relations between tuples? You can do everything with that. Maybe not efficiently, maybe not obviously, but you can do most things. Nowadays, people want to deal with very large objects. Relational databases are designed to deal with tuples that have strings and numbers in them. Nowadays, we want to deal with music and video, similarly large kind of objects. We don't always want to do this precise matching where something is greater than 10. We might want to say where something is like something else. Very large amounts of data so that you can't store it on a single device or even on a local network. You're going to have to splatter it all around cloud or in your own data centers somewhere. Lots and lots of clients and therefore lots and lots of transactions. Solid state storage changes the equation a little bit. And since we need things globally, and since we can't store everything in our local data center, we've introduced a new kind of latency. Previously it was disk. If you had to go to disk, that cost. Nowadays, if you have to go across the network, that's going to cost. And it's going to cost even more than going disk. Of course, not every application needs all of those things. So, what do we conclude from this? That the relational model doesn't work for everything. SQL doesn't work, solve every problem efficiently. And hard transactions aren't necessarily essential for a lot of applications. Of course, there are people who advocate modern databases, and if you looked at that video that I pointed you at last week, the kind of people that advocate those things often say relational model doesn't work for any application and SQL isn't appropriate for anything and hard transactions cares. So they kind of say, well, we don't need relational databases or SQL anymore, and therefore we're going to go with no SQL database. You would all agree with that opinion. And Michael Stonebreaker, as I mentioned last week, he initially said bah to no SQL, but lately he said, okay, it has its place somewhere. Relational has its place somewhere as well. So how have people tried to deal with these things that newfangled applications throw up? Building storage systems that scale massively, designing big data structures that scale massively, changing the kind of data structures that we use. Rather than having tuples, collections of tuples, we now have we can have collections of columns. And how does that change things? Well, I'll talk about that. The two blue things that I've got here are ones that I'm going to talk about. Don't really have time to talk about everything. Other different kinds of operations, we want similarity matching, transactions. Since we can't have everything on our local disk and we can't necessarily write the logs and then write to disk and get our recovery mechanisms working nicely, we may have to put up with a lesser form of consistency, something that happens eventually. And maybe it doesn't matter that we have some inconsistency in the meantime. Of course, there are applications where that does matter, but not all applications. Some people want to deal with databases from the viewpoint of object-oriented programming, and they don't want to have to deal with tuples, because they're not inherently object-oriented, and often objects involve tuples from multiple tables. So a lot of work's been done writing wrappers so that you can program object-orientedly and all of the persistent data lives in the database, and this wrapper does the mapping between what you want and what the database gives you. And then there are various programming languages that have been developed for dealing with large amounts of distributed data and so on. All right. Now I went and looked up what the names of the different sizes of bytes were and discovered that we have terabytes, petabytes, exabytes, which I actually had written as XB last week. Apparently it's EB, zettabyte, and yottabyte. And at least on Wikipedia, there wasn't anything beyond yottabyte. So anyway, the point is that we have very large amounts of data, can't store it in a single machine, and probably can't even store it at a single data center. So what a lot of systems, Google springs to mind, Amazon, web service, anything cloudy, probably has a whole bunch of data centers, and the data is spread across those. But in each of those data centers is going to be a whole bunch of nodes where each node is stock hardware. So it doesn't hold that much, it's kind of like a laptop amount of data. Data items are typically going to be replicated, which as soon as you do that, of course, introduces potential inconsistency problems if one version of the data item is updated and another isn't. And the nodes scattered around the world these days for various reasons, one of which can be that if you put your data center in a different location, it's likely that at any given point in time, one of your data centers, or more than one, is going to be running off-peak electricity costs. So scattering things around geographically, that's one reason for doing that. Obviously, if we have replication, we get more reliability and availability. So if one data center goes down, the other's still there, assuming they have copies of the stuff that we just lost from the data center that went down. You can do optimization, so you can choose the closest data center. And of course, as soon as you've got lots of nodes everywhere, you can parallel execution like I was talking about last time. So that's storing data, storing large amounts of data. Modelling data, or what kind of data models do we need? I mentioned already, some people think relational models, dinosaur, and they'd rather have much simpler models that don't involve much schema floating around in the background, so we can get rid of the catalogue, for example. So key value stores have become quite common. Key is typically some kind of unique identifier, so we've still got that notion floating around in the system that we can uniquely identify something. So that goes out the window in some other contexts, but often it applies here, and the value can be some very large, complicated object. And objects contain links to other objects. So now we have, in relational databases, you have explicit links as well, they're foreign. And if you really want, under this scheme, if you have a whole bunch of objects that all look kind of similar, then you can say, hey, that's a table, or that's a relation. as far as consistency goes, transactional models, if in a classical relational database, as soon as a transaction commits, the persistent version of the data is updated and it's never going to be lost after that. Even in the case of system failure, store it from your transaction logs as we saw. And when a transaction commits, things happen relatively quickly. I've written instantly there, but obviously because you're talking about writing to a disk, there's some finite time before the data actually gets written. But those kind of transactional systems give you a very strong guarantee that your data is not going to get mixed up and inconsistent. A lot of these geographically large applications don't necessarily need strong consistency. The example I give, you might be annoyed if the catalogue shows yesterday's price and that's what you get charged, and yesterday's price happens to be higher than today's price, because if it went the other way, you wouldn't complain. What example? Sort of another example and then promptly forgot it. Oh well, doesn't matter. But in any case, there are plenty of applications where it doesn't matter. The data's not exactly consistent across the whole system. Typically, the update, any changes to the data are going to be started somewhere, and then the change they make has to propagate to all the other copies of the data. At a given point in time, some copies of the data may have been updated, some may not have. So we've got inconsistency if we look across the whole system, but eventually the change gets propagated everywhere. Or if we're talking about distributed consistency in this context, if one of the nodes that is intended to update the data can't, then maybe we wind back the whole transaction, even though it's committed on one machine. It's kind of okay, I've committed now, but I'm not going to fully commit until I know that everybody on the system has fully committed. So at some point in time, the original node has committed the data, so it thinks it's finished the transaction, and it tells all of the replicated nodes that are replicating that data item that they should do the same. At a given point in time, there's going to be inconsistencies. If we subsequently ask a query, then it might be important which version we get back, whether we get the up-to-date version or whether we get the older version. Maybe that does matter, in which case we have an issue of how to decide which node we should look at to get the real data. So that's interesting. So all of these distributed systems have some kind of notion of how we know that a transaction really has committed, and the strongest level of consistency is when the change has propagated everywhere. The weakest level is when the originating node has made the change and no one else has, and then there's intermediate stages where some number of nodes contain the replicated data. Right, so we're going to look at two variations on the theme, column stores and graph databases. Column stores basically still use the relational model, but they store the data differently, and it turns out to be more efficient in some context because of it. Graph databases, on the other hand, thrown the relational model out the window and try to model things in terms of surprise, graph. They're useful for a lot of applications nowadays. Things like social networks always get thrown up. But since they're such prominent applications these days, they are important. And the other, I guess, difference is that there's a very explicit representation of relations, whereas in relational databases, relations are kind of implied by foreign keys. All right, so let's take a look at column stores. So basically, column stores are databases where we organise the data according to columns rather than tuples. Is what we've been looking at for the whole semester up to this point. They're still based on the relational model, so we've still got the notion. We've got a table, and the table has tuples. It's just that the tuples aren't stored coherently like they are in a regular relational database. The values for each tuple are stored separately. Well, the values for the attributes of each tuple are stored separately. So the data is actually stored column by column if you want to look at a relational table. So some kind of applications, particularly offline analytical type applications, work quite well for this kind of storage structure. In fact, it turns out that the ideas for column-oriented databases have been floating around for a while, but it took until this guy did a PhD thesis at MIT and pointed out a whole lot of performance benefits from storing data in columns that the whole started to pick up a bit of prominence. And Michael Stonebreaker got in on the act, and he's been involved in the development of a commercial system, which I think is that, or maybe it's called Vertica. I don't know. Anyway, there's Vertica and there's CStore, and they're related. So here's what things look like. So the file structures, that's what we're used to. We've got a table of tuples, and the tuples are stored exactly like that. So the ID, the name, and the date of birth are stored together. You've seen how do you represent tuples within a page and so on. In a column-oriented store, tuples are stored disparately, if you like, and we've got all of the IDs in one file, all of the names in another file, all of the date of birth in another file. How do they relate, or how do we put them back together again to form tuples? Because eventually that's what we want to do. We're just having a different data storage representation for relational data, but you basically use the index. So the first ID, the first name, and the first date of birth, if you put them together, you get the first tuple. Yeah, you're talking about this. Oh, the ID here was a little bit unnecessary. Well, it's not unnecessary. It's still a primary key. But you can either represent them simply by position. So that obviously creates update issues. If you want to move things around, you can't do that easily. But some other versions of column-oriented stores that I've seen actually stick an ID in front of each of them. But notionally, these are all ID number 1, ID number 2, ID number 3, and so on. Sure. Yeah. Yeah, of course, if you store it like that. But when you sort things, you tend to sort them together anyway. So, and you don't tend to sort the table, and well, you can sort the table and store the sorted version. But if you were going to sort something like this, you'd have to take into account sort on maybe the name column, and then as you were moving the entries in the name column around, you'd have to move the ID and the date of birth at the same time. And in fact, one thing you can do here, speaking of sorting, if you really want, you can store multiple different sorted versions of the table. And a lot of systems will actually take multiple versions of the table, and what they're actually taking is a projection table and storing that as a series of columns. So, you know, in this... Well, they could. Yeah, they could do that. But actually, physically storing them is useful as well. But at query times, yeah, at query time, you can grab them more easily. So you can have multiple projections. And the reason that's not going to cost you so much in storage is another thing that column-oriented stores often do, compression. And it turns out that once you've got a sorted column and you've got all these values, all the common values adjacent, then a lot of the compression algorithms work quite well. Of course, you can't lose data, so you've got to make sure that a column has to appear at least once somewhere. Yep. Not necessarily. Yes, in some senses it will. I'll talk about that on the next slide, because you've got to look at 3 different files if you want to, you know, if you just want to do select star from that relation. Sure, you've got to read 3 different files and reconstruct all the tuples. But often you don't need to do things. Let's see, yeah, and the rows, and this gets back to your point, that you've got to have the related attribute values stored at the same index in each of the files. So we could do something like this, and the reason we've done these projections is we're kind of anticipating queries that are going to be asked. And for example, storing things like this might be useful. In fact, we don't even need the student there. Well, we could use it to get a list of marks for a given course, or compute the average mark for a course, something like that. Storing these tuples would make it relatively easy to compute a student's term WAM. You know, if that was something that we did frequently. And here, if we just want to get roles, students who are enrolled in a particular course, having that kind of information would be having just these 2 columns stored separately from anything else would be a faster way of doing it than reading through a table that had all of the columns in each tuple. Because obviously a course, potentially quite small. Student, if it's an ID, that's also quite small. So a sequence, 2 sequences of small values, we simply have to scan through those together rather than scanning through these things, which they don't look like they're going to be that big, in fact, but they were certainly going to be larger than those 2. All right, so how does columns actually help? Well, one place where it doesn't help, when you're doing insertions, you have to update multiple files rather than just taking your tuple, sticking it at the end of one file. So you've got to split it into columns, stick each of the attribute values into a separate column file. So that's one place where it's worse. If you're doing projection, that's neat because you basically just run down, especially if you're doing select AB from R, where you don't have a where clause, you can just run down the 2 columns and the attribute values together and get tuples that way. So it's pretty straightforward. If you're doing projection on the full table, you'd have to run down all of the tuples in the table. For each tuple, you'd have to extract fields and reconstruct a smaller tuple to go in the output. So it's not really free, but it's certainly a lot simpler doing it for full tuple. In some contexts, selection might require less work than reading whole tuples, because in a row-oriented database, you don't have any choice. You just got to look tuple by tuple unless you've got an index, in which case you've got to look at some tuples. But either way, you've got to look at whole tuples at a time. if you can do what you need to do with the select, and I've got some examples coming up, then maybe you only need to read some of the columns. You don't need to read all of the data just to do the work that you really want to do in the select. And similarly, for joins, you might be able to, and once again I've got an example coming up, but you might be able just to scan the columns that are for the join attributes, and that's presumably smaller than scanning big whole tuples for the two relations. So once again, we saw that some things work slower for column-oriented stores, some things work faster. So which one is going to be better for a particular application depends on the mix of queries and updates. And that, knowing what kind of queries are going to be asked, we've seen that crop up in other contexts where we decide whether to set an index, blah, 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 things like that, depending on the kind of queries that we're going to be asking. And we also saw it in multi-attribute hashing as well, where you decide how many bits you allocate to a particular attribute. So because relational databases say, all right, here's a collection of values, they make a tuple, I'll stick it in a table, that's it. There, in some sense, you could think of it as being a bit optimized writing. Just want to possibly at the end of a table. So they're good for things where there's a lot of updates happening. They might also be better if we ask a query where we need all the attributes, then maybe we're not really going to save that much by reading all the individual columns and gluing them together rather than just reading the tuple. Picking them out. The other thing about column-oriented stores as well is the fact that we are reading multiple files, and if you think how that's going to impact your interaction with the disk, if you're reading a sequence of tuples, you do a seek, you get a page, then you do another seek, you get the next page, you do another seek, you get the next page. If you're reading through 3 files of columns, you do a seek to one file, then you do a seek to somewhere else on the disk to get another column, another page of column values, and then you do another seek. So you're doing more work on the disk for the same, to collect the same amount of information. So that's not necessarily good either. On the other hand, if you've got tuples where you don't need all of the data, if you've got result tuples that don't require all the data from the original tuples, then that's useful. And potentially you can generate small intermediate tuples as well. And the reason I've written tuples there is potentially you can just grab parts of a column, so you're not actually instantiating the tuples necessarily until right at the end. We'll talk about that in a minute. Oh, and the other thing too is now that you've got separate attributes for, or you've separated the attributes for the tuple, if you want to access one column, then one transaction can do that. And if another transaction wants to access a different column, they can both do it and they don't necessarily interfere with each. Of course, if they're making changes like deletions, then there clearly is some kind of interaction has to happen as well. But potentially you can do things in separate columns in parallel. So that could help. It's not necessarily locking. Potential for parallelism. So we've said that some of the columns, probably at least one of the columns in each of the projections will be sorted. That's a useful thing to do, and it's useful because you can compress things well. And of course, we've all seen several contexts when we've been looking at how operations are implemented, that sorting often helps. So if things are already sorted, that's potentially useful. So a couple of obvious examples there from what we've seen before. Of course, an issue, if you're talking about sorting columns, only it's highly likely that only one of the columns will actually be sorted. The other values have to be consistent with the sorted column, but these aren't necessarily themselves going to be sorted. Yeah. That it has to within a projection. Yeah. You don't tend to, the thing is you don't tend to be mixing projections from the same table in a given query. You're likely to choose one of the projections based on, the query optimizer can look and say, hey, this projection here is sorted on this particular column, and being sorted on this column is going to be useful for the join operation. So it's something that, not necessarily going to make things trickier. All right, so let's have a look at how we might evaluate queries in this context. So projection, I keep saying it's easy, and basically you're just doing sequential scan of all the columns in parallel, grabbing attribute values from each, sticking them together, and making a tuple, and then add that to the result. So if we're doing something like this, obviously that's not SQL, it's just to show what schema looks like. So there's going to be columns for D and E as well, but this is one example where that's useful. We don't have to worry about the D and E columns. If this was a row-oriented database, we'd be reading values for the D and E columns even though we don't care about them at all. So we just scan through each column, grab the next value from that column, and as long as we scan through them in sync, we're going to grab the right corresponding values, stick them together, tuple, and add that to the result. So projection easy. If we got a query like this, then even that's potentially useful, and it can be useful, or we can, if you're doing assignment 2, this might look vaguely familiar, but what we could do is we could build a bit vector that tells us which tuples actually match each of these conditions. And we could do that in parallel. We can run down this column, build a bit vector to say that tuple matches, that tuple matches, that tuple matches, and so on. And we can run down the other column at the same time. That matches, that matches, that matches. And then we can add those two bit strings together. That'll give us the overall set of matching tuples. And then we put them together. And this process of trying to do all of the query just using the individual columns and maybe even using indexes from the columns and then putting them together, right, it's called late materialization. So, I thought I had, the next slide is the example of what I just showed. So here's an example of doing it for a single column. So we've got a string of matches. The length of the bit string is the number of tuples in the table. We initialize it to all zeros. Then we run down the column. We make our test. And if any tuple succeeds the test, then we set the corresponding bit in the bit string to 1. And then we can run through the bit string and pull out and form the tuples based on which particular index value match or indicate a match. Doing this scan here is obviously the things that we're scanning here are going to be smaller than whole tuples, and if we're using compression, they might be even smaller. I guess the downside is you're doing 2 passes over the. So that's your first pass, which hopefully is relatively small, relatively quick, and then this pass where you're running down 3 columns parallel. If we're doing this example, then we can do the first, or you can do these tests independently, and I've stuck them in the same for loop here, so obviously we're not getting any parallelism necessarily unless we do these two parallel. But we compute a set of matches for the first condition, a set of matches for the second condition, and then we bitwise AND them at the end. That gives us our matching tuples, and then we run through the columns, build those tuples. Anything wrong? There might be bugs. Who knows? So a whole a bit string full of zeros of the size of the number of tuples, run down the columns from the start to the finish, look at each B attribute, the ith value for the B attribute. If it satisfies, then we set 1. That matches bit string, and we do the same for the D column, and then we'll have 2 bit strings indicating a match on the B attribute, a match on the D attribute, and we AND them together. If it matches on one but not on the other, then that condition fails. It's only if it matches, if both of those conditions have a 1, that we end up with a 1 in the final matches. So it's the kind of thing that you're looking at assignment 2. If you'd started 2, if you haven't, then you wouldn't have stuff. All right, so that's selection. Join. Once again, we don't have to look at the whole tuples, we're just looking at the join attributes. This time we're doing things a little bit differently. So we can still do this as nested loop join or whatever other kind of join that we want to do. But basically what we're looking for is, here's a value here, it's at position number 1. Are there any tuples in here that have the same value? And yes, that one. So that's position number 2. So that gives us that pair of values. So these are now index values rather than actual tuple attribute values. And then we'll look at this one. Are there any 36s? Yes, there are. So we get 2 and 4. Are there any 42s? Yes, there are. So we get 3 and 2. Are there any 44s in this column? No, there aren't. Are there any 38s? Yes, there are. So we get that one. Now, interesting thing about doing things this way is that this column is always going to be sorted because we're scanning through this thing in order and we're grabbing the index value. We go. This won't necessarily be, but it's life. So this is what it's going to look like. So this is where we're doing a join on the A attribute from R and the X attribute from S. And here I've just written it up as a nested loop. So we iterate through the A column from R, and we iterate through the X column from S. We check whether we've got a join, and if we do, then we create that index list. I've kind of written it here as a tuple, but you could equally well do it as 2 separate columns, although I reckon doing it tuple probably slightly useful. So having done that, we found pairs of tuple, or pairs of row positions, if you like, where we've got a match for the join, and then we just run through the list of pairs and we grab the corresponding, and here I'm just grabbing the A and B attributes, but if we want more, then we grab A from R and C from R if it happens to have a C attribute and so on, and build our result tuple for the join. Yeah? Well, it depends. Those columns are certainly going to be smaller. So the process of at least forming this thing is certainly going to be more efficient than doing pairs of tuples. Yeah. You're just dealing with a column with one attribute. So that's where the whole game. I mean, you go and read the papers. They do lots of benchmarking, and they can show that this actually works. I mean, Daniel Abadi did it in his PhD thesis, and that was the thing that really triggered people to go and investigate further and actually build systems like this. In fact, he built a little prototype for his thesis and compared it against a commercial database, and on some of the examples it was an order of magnitude faster. So it involves a number of optimizations, including compression, to make the amount of data that you're even smaller, but beat commercial systems, which made people sit up and take notice. Right, for things like aggregation, typical aggregation operator works on a single column, and hey, what do you know? We've got single columns, so you can just run down the column of marks and compute the average. And in parallel, you can run down the column of students and count them up. So that's handy. So aggregation actually works out quite nicely. If you have to deal with groups of columns, so you've got expressions like A plus B plus C or something, then you tend to have to group things, and you can't necessarily do the late materialization idea. So you can't necessarily just deal with index. You may have to put them together earlier in the query evaluation process. So that's potentially going to end up being a little bit slower. Certainly, if you can do things independently, you can do them in parallel, and that's going to be fast.